In this section, we'll cover the method of data normalization, a popular data analysis technique. An English guy by the name of Edgar F. Codd introduced the concept of normalization while he worked at IBM in the USA. Initially, with his invention of the relational model in 1970, he identified what's known as first-form normalization, and then in 1971 added second and third-form normalization. We'll talk about these in this section. There are additional normalization forms, but I'll stop at third in this tutorial. I class data normalization as a bottom-up method of defining entities because it works at the detailed data element level to discover entities and assign their data elements. However, it can also be used as a verification process for the results of top-down information analysis. Here's what we'll cover in this section: definition of normalization, first-form normalization, second-form normalization, third-form normalization, forming an ERD from third-form normalization results, and the benefits and limitations of normalization. Now, this section does seem to be a little technical, although I hope I've made the examples I show understandable and applicable to the business world's general audience. First, the definition of normalization. Here's my succinct definition: to ensure that any data element has only one value for an occurrence of the entity it describes. In more technical terms, it is the process of determining the highest level of data independence possible by ensuring that any one occurrence of an entity can have only one value for a data element, and that a data element is dependent on and describes the correct entity. For example, the name Brian Dickinson appears only once as a customer name in a customer entity. Normalization is a specific technique which can be applied after top-down information modeling, but is better done during modeling to reduce the impact of change. Normalization is built on the relational approach, which uses relational tables. The rows in a table represent a set of data elements which are related in some way. The columns in a table contain occurrences of values for a data element. I'm going to use this example on the screen through this section. One result of normalization is third-form normalization, which forms the simplest, most stable groupings of data elements. Lo and behold, it's achieved in 3 steps. I want you to picture a warehouse parts location file. Throughout this section, I'm going to use a dialogue with the warehouse staff to show my examples. The first statements from the staff are: I have my parts location file containing a folder for each part we sell. Each folder has a location record which I use to locate the bin number for a part in our many depots. On the screen is a depiction of some of the folders with their content. There are location records for parts. We can see repeated sets of information, such as location records themselves are the major repeating group, and within each location record, a list of depots is repeated for where a part is located. If a data element, or a set of data elements, is repeated, then we call it a repeating group. We can also see redundant information, such as supplier name. Of course, if a supplier changed its name, say it merged with another company, then many of the records would have to be updated. Let's conduct the process of first, second, and third form normalization on this parts file. First form normalization makes us separate out repeating data elements, or sets of repeating data elements, repeating groups, so that each cell, data element, in our table contains a single value, no null values. As an information analyst, I might say, so looking at your parts record, it appears you need a part number and a supplier name to get to the lot numbers, the sell-by dates, and the reorder lead times, and the depots and bin numbers, right? And I can show a sample set of records shown here. Note, I'm going to show any access key in yellow in my examples. The staff response may be yes, except each of our depots has its own bin layout and associated bin numbers. So acknowledging this, we can separate out the repeating group of depots as shown here. Whenever we separate out an internal repeating group, we keep any keys necessary to get to that repeating group of data elements. In other words, we compound any necessary keys. As shown, we now have 2 sets of data. The one on the left shows that we need part number and supplier name to get to lot number, sell by date, and reorder lead time. The one on the right shows that we need a compound key of part number, supplier name and depot to get to the bin number. Even though some key data elements are shown twice, there's not really any redundancy, as they may turn out to be pointers. Remember my invisible strings in the relationship section? Now we can conduct the process of second form normalization. Our input must be in first normal form, and each data element in a table must be fully functionally dependent on the whole key. Now a data element is fully functionally dependent if we see a change in its value when the value of any of the key data elements changes. So back to our dialog. The staff statement says, because we deal with degradable materials that have a shelf life once they're delivered, we must assign a lot number and a sell-by date to each load of parts from a supplier. And unfortunately, part numbers are not standard across suppliers, so we need both the part number and supplier to get to the lot number and sell-by date. So using the relevant set of data from first form normalization, we can display the result of that statement. The image shows that the keys part number and supplier name are needed to get to lot number and sell-by date. Now our response could well be, what about reorder lead time? That's in the set also. If the staff responds, no, that's dictated by the supplier, it seems to depend on where they're shipping from. We could clarify that statement by asking, so the reorder lead time is dependent on just the supplier. No doubt that would elicit a response something like, that's what I just said. We would then separate out a small set indicating that just a supplier name is needed to get to reorder lead time. You can probably see that having a separate list of suppliers and their reorder lead times would reduce the number of updates needed to many location records if a supplier changed its lead time. Going back to our definition of second form normalization, you can see that reorder lead time was not fully functionally dependent on the compound key of part number and supplier name. Just supplier name was needed. This brings up the subject of what's known as an update anomaly. We can see that if at some point we remove the last location record in the old file for a part from a particular supplier, say we were temporarily out of stock on that item, then we would lose the reorder lead time for that supplier. By separating out this small table of suppliers and their associated reorder lead times, we don't lose that data element's content. The other table from first normal form had one data element that was already functionally dependent on a compound key. So the result so far from second normal form has three tables. We need part number and supplier name to get to lot number and sell-by date, and we need supplier name to get to the reorder lead time, and we need part number, supplier name and depot to get to bin number. Now, we can conduct the process of third form normalization. Our input must be in second normal form, and all data elements must not be dependent on any other data elements, termed a transitive dependency. In other words, each data element must be dependent on nothing but the whole key. In my business, I may find a seminar record containing the students in that seminar and also see the student titles. However, a student title is not dependent on the seminar key, it's just dependent on the student key. So back to our dialog. We may ask, you told me sell-by date and lot number are determined by part number and supplier, right? The staff may respond, no, I didn't. I said that we assigned a lot number and a sell-by date to each load of parts when they come in from a supplier. But if you're asking me what makes me determine a sell-by date, it's assigned to a lot number when the parts are unloaded. We could clarify that statement by asking, so really lot number determines sell-by date? No doubt that would elicit another obvious response, something like, that's what I said before. So using the relevant set of data from second form normalization, we can display that statement. Notice how we have a non-key data element determining the value of another non-key data element, because they were both linked to the same original keys. That's a transitive dependency. So now we form two tables. One shown on the lower left indicating that a part number and a supplier name is needed to get to a lot number, and one shown on the lower right indicating that a lot number is needed to get to the sell-by date. So here's the result of applying third form normalization to our parts location file. These four sets of data have no redundancy and are considerably easier to update when business policy changes. As I said before, depending on our implementation of these tables, there may be no duplication on even the key data elements, as they can become pointers. So every data element in these tables has only one value for an occurrence of the entity it describes, which was our goal stated at the beginning of this section. I remember the goal of normalization in my mind with the phrase, data elements are dependent on the key, the whole key, and nothing but the key, so help me cod. Oh well. It's worthwhile stating that any process or query that was accomplished with the original parts location records, in my example, can be done with these tables, without any redundancy and update problems. Finally, the resulting tables, sets of data elements, should be assigned entity names. The relationships should be extracted from the business policy used to create the original records, as well as from compound keys in the resultant tables. Using the relational tables from third form normalization, we can form an entity relationship diagram that will show the resultant entities and the relationships formed from the table's compound keys. Notice I've used what I call the event level ERDs, that is, the relationship and cardinality reflects the use based on the lookup needed in the original staff statements. So depending on the query of the staff, one part with one supplier is needed to retrieve the depot. That gets the staff to the bin number. Of course, just a lot entity is needed to get to sell by date. And just a supplier entity is needed to get to reorder lead time. For the organizational view, we can show that a part can have many suppliers and a supplier can have many parts. Of course, depending on the staff needs and implementation, other tables can be formed, and we can even denormalize for efficiency reasons at design and implementation time if necessary. As a summary, let me state what I believe are the benefits and limitations of normalization. First, the benefits. Third form normalization offers a step-by-step cookbook approach to discovering and partitioning entities. It is useful for checking and verifying the emerging information model. It may provide insights not otherwise obvious from existing files and staff interviews. And the limitations I see are, it is difficult to tie entity types to relationships if no naming standard was or is in place for the keys. In other words, we need to have the same key in two records to know it's the same table. As I mentioned before, some old file may be keyed on customer name, while another could be keyed on customer number or even social security number. It is important to know the definition of each data element, especially when looking for transitive dependencies. In our example, reorder lead time for the part was dictated by the supplier. Do not try to normalize from individual reports, screens, etc. These are typically specialized implementation views and will probably bring together data flows instead of only stored data. Plus, you may find masses of reports and waste time applying third form normalization to each. Finally, the procedure can be quite time-consuming with voluminous input, so it's best to build normalization in during top-down information analysis. There is also additional normalization forms, such as Boyce Codd normal form, sometimes referred to as 3.5 normal form. However, third form is most commonly performed in data analysis. I hope that section wasn't too technical for those not already familiar with database concepts. And please remember, I do not use information analysis as only a precursor to database design. It can just as easily be used for manual file design.